Kinematics in 1 and 2 dimensions. Position, denoted as x, specifies the location of an object along a straight line. It's a function of time, represented as x of t. Displacement, or delta x, is the change in position and is calculated as the final position minus the initial position. Velocity is the rate of change of position with respect to time. Average velocity is delta x over delta t, and instantaneous velocity is the derivative of position with respect to time. Acceleration is the rate of change of velocity with respect to time. Average acceleration is delta v over delta t, and instantaneous acceleration is the derivative of velocity with respect to time. For motion with constant acceleration, the following equations apply: v equals v0 plus at, x equals x0 plus v0 t plus 1/2 at squared, v squared equals v0 squared plus 2a times x minus x0, and x equals x0 plus 1/2 times the sum of v and v0 times t. Here, x0 is the initial position, v0 is the initial velocity, and t is time. A special case of one-dimensional motion is free-fall motion, where acceleration is due to gravity, approximately 9.8 meters per second squared downward. The equations for free-fall motion are: v equals v0 minus gt, y equals y0 plus v0 t minus 1/2 gt squared, and v squared equals v0 squared minus 2g times y minus y0. In 2 dimensions, position is a vector describing the location of an object in a plane. It is given by r equals x of t times I hat plus y of t times j hat. Displacement is the change in position vector, and velocity is the rate of change of the position vector. Its components are the derivatives of the position components with respect to time. Acceleration is the rate of change of the velocity vector, with its components being the derivatives of the velocity components with respect to time. For motion with constant acceleration in 2 dimensions, the equations are: Vx equals v0x plus axt, Vy equals v0y plus ayt, x equals x0 plus v0xt plus 1/2 axt squared, y equals y0 plus v0yt plus 1/2 ayt squared, vx squared equals v0x squared plus 2ax times x minus x0, and vy squared equals v0y squared plus 2ay times y minus y0. Here, x0 and y0 are the initial positions, v0x and v0y are the initial velocity components, ax and ay are the acceleration components, and t is time. A special case of 2-dimensional motion is projectile motion, assuming no horizontal acceleration and a vertical acceleration due to gravity. For horizontal motion, x equals v0 xt. For vertical motion, y equals y0 plus v0 yt minus 1/2 gt squared. The velocity components are vx equals v0x, and vy equals v0y minus gt. The trajectory equation, eliminating time t, is y equals y0 plus v0y over v0x times x minus g over 2 v0x squared times x squared. When analyzing relative motion between 2 reference frames, use VA/B equals VA minus VB. If frame B is moving with velocity VB relative to frame A, the velocity of an object observed in frame B is v object/B equals v object minus vb. When an object moves in a circular path with constant speed, it has centripetal acceleration, given by AC equals v squared over r, and centripetal force, given by Fc equals m times v squared over r. The tangential velocity is given by v equals 2 pi r over t, where r is the radius and t is the period. Let's go through some practice problems. One-dimensional motion. A car accelerates uniformly from rest to a speed of 20 meters per second in 5 seconds. Find the acceleration and the distance covered. Projectile motion. A projectile is launched with an initial velocity of 20 meters per second at an angle of 30 degrees above the horizontal. Calculate the maximum height, time of flight, and range. Relative motion. A boat is crossing a river with a velocity of 5 meters per second relative to the water. The river flows at 3 meters per second. Determine the resultant velocity of the boat and the angle at which it must be steered to cross the river directly.